All right. Good morning, everybody. Hi.
Good morning.
Morning. Happy Tuesday. Happy first full week of October. Hopefully we get some rain soon so it'll feel like it. And let's jump in. So today we're going to be talking about what's called the carbon cycle. It's the cycle with which carbon dioxide and carbon as a whole cycles throughout the Earth system. And so I thought a really good warm-up question would be having people take a moment and think about one thing that adds carbon dioxide to the atmosphere, and then one thing that people think removes carbon dioxide from the atmosphere. So the link to answer that question is right here. And go ahead and give it your best shot, and then we will talk about it. All right, for those who have just trickled in, let me click on that link again, or let me post that link again. Absolutely. All right, a few more people have come in, so I will paste the link one more time. And take about another minute. Mm-hmm. Looking good. Mm-hmm. Alrighty. A couple more people just trickled in. Just take a few more moments. And then we'll take a look and see what people are saying. Kind of looking at the answers right now, and they're looking very nice. Alrighty. I know people are still typing in answers, so you can continue to do that. But let's take a look and see what people are saying so far. So, what are some things that add carbon dioxide to the atmosphere? Breathing. Correct. We inhale oxygen, we exhale carbon dioxide. Fires due to carbon being emitted from the smoke. So when you burn any kind of biomass, such as forests, trees, bushes, grassland, that's actually all made up of carbon. And so when you burn that, it reacts with oxygen to produce carbon dioxide. Absolutely. Gas fuel cars, fossil fuels, smog, living creatures such as us, organisms respire or decompose. That's something else that happens too. Unfortunately, we're all going to die someday. I'm sorry to break that news to you, but in that process, a lot of the carbon that our body is made up of decomposes, and part of that reacts into carbon dioxide and methane. Deforestation, fossil fuels, humans, non-electric forms of transportation and factories, so human activity. Human activities, fossil fuels, forest fires, driving a car, cars emit carbon dioxide, deforestation, car pollution, burning of fossil fuels, greenhouse gas emissions, car emissions, burning wood, cars, people. Excellent, nice and comprehensive. Did a good job bringing up a bunch of different stuff that adds carbon dioxide to the atmosphere. Those things are what are called carbon sources. So anything that adds carbon dioxide to the atmosphere is what we call a carbon source. Now, what about something that removes carbon dioxide from the atmosphere? This one I think was a little bit more lopsided, because usually when people think of something that takes carbon dioxide out of the atmosphere, the first thing that comes up, plant activity. Bingo. Photosynthesis, trees, plants, trees, photosynthesis, trees, photosynthesis, absolutely. Planting more trees. So let's see here. Doesn't the ocean remove carbon dioxide from the atmosphere? Yes, it does. And there's actually something very concerning about that too. So basically carbon dioxide reacts with water very easily to form what's called carbonic acid. Essentially what we are doing is we are carbonating our ocean. Rain. Yeah, in fact, I'm actually going to talk about that today, how rain removes carbon dioxide from the atmosphere. Plants, trees, photosynthesis, trees, the ocean, algae, nice. Okay. Well, excellent. So what you've all just done right now is you have all just provided several key components to what's called the carbon cycle. And that's what we're going to talk about today. So today we are going to talk about the carbon cycle. Before we do get into that, I do have a little bit of business I need to talk about real quick. And let me move over here. Okay. So now that homework 2 has been graded, and I had a chance to look at what Tyler said, what Tyler put down, which I thought was exactly what I would have put down. So I thought he did it and said it very well. That being said, one of the things I noticed was a common thing was that first question or two may have been a little bit more unclear than I had intended it to be. And I have no problem owning up to that. If a question I ask or if something I do doesn't come off as clear as I intended, I'm always a big fan of making that right. So what I've actually done is, for those of you who got less than a perfect score on the homework, I actually put together a little opportunity, a few different questions that you could actually submit to get those points back. And that's just the way that I want to make sure that, you know, any ambiguity in a question that I ask is made up for, because I really do want to make sure, more than anything, that I'm giving everybody a good chance at being successful and just doing what I can to help. So I did just put that up on Canvas probably 10 minutes ago, right before class started. And you have a week to complete it. It's based on the same graph. And basically, the big questions I'm asking for there are, one, looking at the graph a little bit more, how often do we get those peaks, those times where temperature and carbon dioxide are higher than normal? And then the second thing was comparing the peaks in carbon dioxide to our current carbon dioxide concentrations, and why that might be a scary comparison. One other thing I'll mention, for a couple of people who had problems uploading the homework assignment, I had one or two people say that they had a problem uploading the homework assignment. Those haven't been graded yet. If Tyler put a 0 in the grade book, that's just because I haven't gotten around to grading it yet, or because I know a few people had to email me their assignments. And so I'm actually going to get those graded and in the grade book today. So I do apologize for that. One thing I'll be very clear about is Tyler was doing my bidding. So he did exactly what he was supposed to do. So I just want to make sure that any tomatoes that need to be thrown at me. Because, yeah. So the other thing I'll be doing is, between now and hopefully the next class, I'll also be grading our quizzes and getting those back to you soon as well. All right, do you have any questions, comments, concerns, threats? Anybody want to throw me off a balcony right now? I understand if you do.
Sorry,
But
I had a question. I mean, it was specifically to my work. Because I was having difficulty, and I know that I emailed it to you, but I think that in the process of me like trying to turn it in on Canvas and trying to email it to you, one of the sections of my work got deleted because I know I had to remake my PDF a bunch of times.
oh no.
So I got like a point, I think, knocked off, and I was wondering if I could include that because I know that I did it, and then
Of course.
Okay, thank you.
Yeah. And that goes for anybody. If you look back at your submission and you see something that didn't quite look right, let me know about that as well. And then somebody just asked me, if we do bad on the quiz, is there any way to earn some of those at all, to earn some of those points back? So what I'm actually going to be doing in the next week is actually getting some extra credit together as well. And I do also drop one of the lowest quizzes. So those are a couple of ways that I kind of allow a little bit of leeway for a rough quiz score. So there is some extra credit coming. I usually don't assign it till the second half of the course, which we're now getting towards. So I'll just say that, yeah, but yeah, I will be assigning some extra credit in the next week or two, and I do drop one of the lowest quizzes. So you will have a chance to redeem if anything went wrong. On the homework 2 assignment, it says no content. Somebody just messaged me that. So, okay, let me actually go back and just double check. I just uploaded it, so it might have. So it's actually down under week 8, under this week. I actually just put it under this week. And the redo itself is labeled homework 2 redo.pdf. And so that should have the homework questions themselves. And then I haven't typed anything in the submission link. I just put a link up where you can upload it. That was just because I had to rush it. But that being said, I can go in there and put some additional directions. So does the midterm cover everything we've seen up to date? Yes, it does. But it's heavily going to be based on the first 2 quizzes and the first 2 homework times, or first 2 homeworks that we've done, which I will make sure I have answer keys for everything up by Thursday, as well as a study guide by Thursday. Does that help answer that question? Absolutely. Absolutely. And then if you have any other questions, comments, concerns, please let me know. I just want to do what I can to help. And you know, if something ends up being unclear, my goal is to demystify it, to clear it up. So never hesitate to ask, and never hesitate to reach out to me if something doesn't make sense, if you're upset about something. For me, it's like being able to help is what I care about. All right. So that being said, if you do have any more questions, you can either drop them in chat, or you can hang out for a few minutes at the end of class, and I can help answer those questions. Otherwise, our participation points in the grade book. Oh boy, that's my fault. Okay. I will put them in this afternoon. So if you've been coming to class, you've been turning these things in every day, you're good. But yeah, I need to put those in the grade book today. I'm so sorry about that too. But yeah, no, I will actually put that in today. I apologize for that. Okay. So other than that, I do actually have them all logged in. I just need to put them, I just need to actually put them into Canvas. That's okay. The midterm is worth 100 points. And like I said, I will have a study guide together for that in the next day, by Thursday. And then is there anything else I could help with for the moment? I'm actually going to take care of that as soon as class ends. Yes, there will be a study guide. There will be a study guide. All right. Absolutely. I'm happy to help, and thank you for, thank you for all for reaching out to me with any concerns or questions you have. So let's jump in. Now that we've got at least some business out of the way, let's jump in to what we're talking about today. So what we're talking about today is these different components of what's called the carbon cycle. And then we're going to talk about some of the different things in the Earth system that actually contribute to the carbon cycle and their roles, including roles called sources. Those are things that add carbon dioxide to the atmosphere. Sinks, those are things that, I don't have a plant near me, but those are things that take in carbon dioxide. And then these things called reservoirs, things that hold on to carbon, that actually hold on to carbon. And in a very real sense, we as humans are also carbon reservoirs. And then I'm going to talk a little bit about the short-term and long-term carbon cycles. And this will actually uncover one of the reasons why fossil fuel use and greenhouse gas emissions are actually a really concerning thing. All right, so let's talk about this. So before I talk about the carbon cycle, just to set the stage, how many of you have ever heard of the water cycle before? Sorry. All right, a few people have heard of the water cycle. I'm seeing a few hands going up. Those of you who have your webcams on, thank you so much. Yeet, I agree. I love it. And well, the water cycle is basically how water cycles through the Earth system. So how it goes from the hydrosphere, Earth's oceans, to the atmosphere, to land, and to life, these different components of Earth's system. And so in a very real sense, the carbon cycle is pretty much the same thing, but instead of it being for water, it's for carbon. Here's how the carbon cycle looks like. And it may look a little overwhelming seeing all these different components to it, but don't worry, we're going to break it down. And basically what the carbon cycle does is it just outlines and it just shows how carbon is removed, added to, and stored by the different components of the Earth system. And it's affected by all these different components. For example, if we cut down a bunch of trees and replace them with cattle, that has an impact on the carbon cycle. You've just removed something that takes carbon dioxide away, and you replaced it with something that adds methane to the atmosphere. And so it's affected not just by the atmosphere itself, but by other components of the Earth system. And the carbon cycle has two main legs to it. It has the short-term leg and the long-term leg. The short-term leg is relatively, in geologic and scientific timescales, really, really short. As in, right there, that was quick. Versus the long-term cycle, which actually involves processes that take millions and millions of years to actually be completed. But each component of the carbon cycle is vulnerable to human activity. And as a result, we need to look at each component of the carbon cycle to determine what are we disrupting and what are the consequences of the disruption. So that being said, let's first talk about the star in this cycle, carbon. Carbon is actually the fourth most abundant element in the entire universe. It's also what we are based out of. How many of you have ever been told we are carbon-based life forms? We are carbon-based life forms. What that really means is that the center point, the building block, the key thing that we are made up of is carbon. Everything organic has carbon in it. Even before it has water, it has carbon. So carbon is an essential component of all life on Earth, and it's an essential component of pretty much the planet itself. And then, as I said, it's the fourth most abundant element in the universe. So, including things like fossil fuels and DNA. So, the genetics in your body are carbon-based. They're based out of these little strands of chains of proteins and of carbon. And proteins are actually made up of carbon. And this carbon doesn't stay put. Just like in the water cycle, water doesn't really stay put. Carbon doesn't really stay put either. Carbon processes can cycle our carbon can cycle through many different components of the Earth system. And where do we find carbon? We find it in all living things. So as I mentioned, life here on Earth is carbon-based. We find it in our atmosphere, both as carbon dioxide, as methane, and then there's actually some molecular carbon as well. And in different geological artifacts and rocks, a lot of the artifacts, a lot of the geological rocks, limestone, are also at least somewhat made up of carbon. And then in fossil fuels, that one is the more, one second here. There we go. And that whole idea, in fact, when you hear the term fossil fuels, a fossil fuel is very much what it's based off of. Or very much what it is. It's dead organic material. So fossil fuels like coal are also where you see carbon. If any of you have a diamond ring, that diamond is a lump of carbon. I know it's crazy. You pay exorbitant prices for the fourth most abundant element on Earth. You can get a single lump of carbon at a store for thousands of dollars, or you can buy a big bag of charcoal for $5. Kind of funny if you have me think, or if I think about it. So where is carbon? If you've ever had sugar before, sugar is made up of carbon. It exists also in the atmosphere, primarily as carbon dioxide and methane. In living things, plants and animals, as well as the different sugars that we consume to provide fuel for us. It's also found in the proteins and the fats that we consume. So when you're eating food, like, you are literally eating carbon. And then soils as well. There's carbon trapped inside soils in the forms of just regular carbon, just regular molecular carbon, as well as methane. In some soils, there's a lot of methane trapped. And then as oceans are in the oceans, a lot of carbon dioxide is dissolved in the ocean. And one of the concerning things is that as we add more carbon dioxide to the atmosphere, a lot of it does get outgassed into the ocean. And as it reacts with ocean water, as I mentioned earlier, for those of you who are here, it converts into what's called carbonic acid. If you've ever drinking anything carbonated, like I have a bubbly right now, and you feel that tingle, some of that is because of the fizziness of the carbon bubbles, but some of that is also because you're actually acidifying the water. In a very real sense, when you add carbon dioxide to water, you are acidifying it. So where's most carbon found on Earth? So these different components of Earth's system. And here are the big locations. The biggest location is the deep ocean. So most of the carbon on Earth is trapped well down in the depths of the ocean. Over 81%, just there. In second place come fossil fuels themselves. In third place, soils. Then a good chunk of it in the surface ocean as well. And then we get into the atmosphere, life, vegetation, and so on and so forth. You don't have to memorize this at all. Just know that the bulk of carbon on our Earth is in our deep ocean. Other than our deep ocean, the bulk of it is in fossil fuels, which the carbon from millions and millions of years is trapped in these fossil fuels, as well as soils, and the atmosphere. So these are where most of the carbon on Earth are present. That being said, one of the things about carbon here on Earth is that carbon is not created or destroyed. So there's actually a finite amount of carbon here on Earth. And yes, we do actually get some stuff that ends up coming to us from space. But when you actually consider how much stuff actually comes from space compared to what we actually have here on Earth, anything we get from space is negligible. So that being said, the law of carbon conservation actually does apply pretty well. It actually does fit pretty well. And the law of carbon concentration, oh my gosh, Tuesday brain. The law of carbon conservation basically states that the carbon that is here has been here since Earth formed 4.5 billion years ago. Carbon doesn't increase or decrease. That's the main component of carbon conservation. We can't add carbon, we can't destroy carbon. So the amount of carbon that we have here on Earth, in the Earth system, is pretty set. It's pretty set. Now this carbon is exchanged between different components of the Earth system. So I've been talking a lot about different components of the Earth system. In a moment, I'm actually going to tell you what they are. But carbon is just like how water is cycled through different components, through the ocean, then the atmosphere, then the land. Carbon does the same thing. Carbon is exchanged from one component to another, then to another, then to another. And that process just continues and continues and continues. Now that being said, I've mentioned these different components of the Earth system, or I've talked a lot about them, but what actually are the components of the Earth system? Well, we actually call them the spheres of the Earth. So these 5 components of the Earth are all what we call spheres. And that's just more of a nickname than anything, but if you actually look, the name itself, you'll see sphere at the end of each one, like atmosphere. And so the Earth is made up, of 5 components, of 5 key systems, 5 key spheres. The first one is the one that we've been focused on, the atmosphere. The atmosphere is what Earth's air is. So the atmosphere is made up of Earth's air. This is where weather happens. This is where, this is actually what allows us to take water from the ocean, desalinate it, and rain it down on another location. So that's actually something we can kind of be thankful for. The geosphere, also oftentimes referred to as the lithosphere, this is Earth's land. So if you get an earthquake, that earthquake has happened in the geosphere. Crust, mantle, outer core, inner core, that's geosphere. So the solid component of Earth. The third component of Earth, life, things, animals, bacteria, plants, viruses. I guess there's still kind of that debate about whether or not they're life. But all the different living components are part of the biosphere, and that includes us. We are a part of the biosphere. Then there's the hydrosphere. That's Earth's water. That includes all the oceans, the rivers, the lakes, the streams. That includes both fresh water and salty water. Now, oftentimes, Earth scientists actually do take one subset from the hydrosphere and give it its own designation, and that would be the cryosphere, Earth's ice. So depending on which textbook you're reading or which earth science you're talking to, many times they'll actually put the cryosphere inside of the hydrosphere. They'll actually say it's a component of the hydrosphere. But that being said, for the sake of this class and for the sake of the stuff I have you read, these are the 5 spheres. So the cryosphere and the hydrosphere are separate for the sake of this. So all of that said, there are 5 main components of the Earth system. The atmosphere, that's Earth's air. The geosphere or lithosphere, that's Earth's land. The biosphere, that's life. The hydrosphere, that's water. And the cryosphere, that's ice. So these are the 5 different spheres of the Earth. And each one of them, including cryosphere, believe it or not, each one of them actually plays a key role in the storage and transport of carbon. And so each of these spheres, each of these components is a crucial element of the carbon cycle. And if even one of them were to be removed, that would throw the whole system out of balance, and that would create lots and lots of problems. Thankfully, nothing on Earth is doing that right now. Oh, wait. Who has 2 thumbs and is ruining the carbon system? Oh, my other thumb didn't show up, but all right. So just some examples of where each one of these is present. So if you actually take a look at inside the lithosphere, that's where we get diamonds from. That's also where we dig up our fossil fuels. Down here, all these cows burping and farting methane, and themselves also made up of carbon. That's carbon in the biosphere. Over here, factories burning stuff and pumping out smoke. That's adding carbon to our atmosphere. Our oceans, and in fact, the fact that they're even green indicates that there's life inside the ocean, even at the surface. Algae, phytoplankton, those are carbon-based life forms, and those are a key element of exchanging carbon dioxide with the atmosphere ocean. And then finally, the cryosphere, believe it or not, buried in much of this ice and in much frozen tundra and in permafrost are big bubbles of methane and other carbon things, but mostly methane. And one of the things we're concerned about is if the ice melts, that methane will be burped out. That's something to be worried about. So all of these different components play one of 3 roles. Either something that adds carbon to the atmosphere, something that takes carbon away from the atmosphere, or something that simply holds on to, contains, withholds carbon. And so each one of these 3 things has a designation. Something that holds on to carbon, kind of a big bank for carbon, are what we call carbon reservoirs. These are things that hold on to, store carbon for a prolonged period of time. So when I mentioned earlier, 81% of all the carbon on Earth is within the deep part of the ocean. That is a gigantic carbon reservoir. That is a gigantic carbon reservoir. Then carbon sources. These are things that add or emit carbon. These are things that actually put carbon into a reservoir. So every time you breathe, you are actually adding carbon to the atmosphere. Every time you breathe, you're adding carbon to the atmosphere. Right now, as we speak, the ocean, when those waves are crashing, some dissolved carbon dioxide ends up precipitating back out and outgassing into the atmosphere. So those are carbon sources. On the other hand, I just exhaled a bunch of carbon dioxide, a bunch is shooting out of me right now as I'm speaking. Well, out in my courtyard, out in different components or different places of this apartment complex and parks around me and so on are lots and lots of plants. Those plants take the carbon that I just exhaled and they absorb it using sunlight that convert it to sugars. That is a carbon sink. That's something that removes carbon from a reservoir. So a carbon reservoir is something that holds on to carbon. A carbon source is something that adds carbon to a reservoir. A carbon sink is something that removes carbon from a reservoir. So a good example of a reservoir would be our atmosphere. When I exhale, I have become a carbon source. I have added carbon to that atmosphere. Meanwhile, the plants all around, they take that carbon out. They are a carbon sink. So that's just one example of these different components: carbon reservoirs, carbon sources, and carbon sinks. Now, there are many different important carbon reservoirs. The atmosphere, as I just mentioned, is a carbon reservoir. Buried organic material. So this is actually where fossil fuels play up, or this is where they play a role. I think I've already broken this bad news to all of you. We're all going to die someday. In one way or another, we're all going to die someday. There's many things that can happen to the carbon in our bodies after we die, but assuming that you're buried, that means that your body is now below ground. Over millions of years, more stuff's going to get trapped on top of that. And basically, the carbon in your body is going to become compressed and it becomes a fossil fuel. So when I say buried organic material, that's what I'm talking about. Buried dead things. And then permafrost. So in our tundra-friendly areas of the world, parts of the coastal part of Antarctica, parts of Alaska, parts of northern Canada, there's a lot of what's called permafrost. Basically, it is, in essence, permanently frozen land. And trapped inside that permanently frozen land is a lot of methane. And the source of that methane is centuries and centuries of bacterial decomposition. Normally that stuff would outgas into the atmosphere, but in those particular areas, because the ground itself is frozen, it's a lot harder for methane to escape. Now, if we were to thaw those permafrost areas, we were to allow that ground to thaw, all of that stuff would just shoot out into the atmosphere. So permafrost holds a lot of methane. And then, as I mentioned, our oceans. Now, this right here looks pretty overwhelming, but let me actually walk you through what's going on here. So what this actually does is this actually shows annual rates of exchange for how much carbon is actually in the Earth system. So wherever you see a yellow or a red number, that represents a rate of carbon exchange. Wherever you see a white number, that represents approximately the total amount of carbon that's there in gigatons. So a gigaton is 1 billion tons. Yeah, mega's 100, or sorry, mega's a million, giga's a billion. Kilo is 1,000. Okay, so as I've mentioned before, the primary carbon reservoir here on Earth are our oceans. The deep ocean in particular has the lion's share of Earth's carbon. If you look at all of the other components of the Earth system, yeah, the deep ocean is by far the biggest component. That being said, there's actually not a whole lot of exchange that occurs relative to how much there actually is. Every year, only about 2 gigatons of carbon via sedimentation are actually added to our deep ocean. And I'll explain how that happens in a little bit. But our upper part of the ocean, the surface part of the ocean, definitely exchanges a lot more. It definitely exchanges a lot more. And then over here, if you actually take a look, these are the different exchanges between plants, life, soils, and the atmosphere. What I actually want you to focus on, though, the main thing I want you to focus on right now are these red numbers, because these are actually what really matter. Well, all of this matters, but in terms of understanding and unlocking the science behind climate change, these red numbers are what matter the most. Whenever you see just a flat number like this, or flat number, gosh, that's a terrible term, something that is a source for the atmosphere, that represents something that is being added to the atmosphere. Every single year, we are adding, as humans, approximately 9 gigatons of carbon dioxide to our atmosphere. 9 gigatons. That is a lot of carbon dioxide that we as humans are adding to the atmosphere. Now, the good news is that Mother Nature has actually been good with at least removing some of that. Approximately 2 of those 9 gigatons are being added to our ocean every year. Now, the problem with that is we are now adding more carbon to our oceans than are actually being removed from our oceans. So that is a problem there, because we're actually adding excess carbon to our oceans, and that's what's causing our oceans to acidify. On the other hand, 3 of those 9 gigatons that we pump into the atmosphere are also removed via photosynthesis. But unfortunately, both of these things, absorption by the ocean as well as photosynthesis, these main 2 carbon sinks from the atmosphere, these main 2 ways that we remove human emitted carbon from the atmosphere, unfortunately, neither of them can keep up with how much carbon we are adding to our atmosphere. We're adding 9 gigatons every single year. Meanwhile, photosynthesis is removing 3 of those 9 gigatons. The oceans are removing an additional 2 gigatons. So we are adding 9 gigatons a year. Meanwhile, we're only removing, or these natural processes are only removing 5 of those 9 gigatons. Only removing 5 of those 9 gigatons. So that being said, every single year, about 45% of what we as humans emit into our atmosphere stays there. And that is why carbon dioxide concentrations are going up. We are putting more carbon dioxide into our atmosphere than these natural processes can take it out. We're adding it faster than they can remove it. We're adding more than they can cope with. And that's why there's this excess carbon budget. There's this excess of carbon in our atmosphere. Now, one of the things I think a lot of people get confused about when talking about emitting carbon dioxide is they'll say things like, wait, so you expect us to not emit any carbon dioxide at all? Does that mean I can never breathe again? And then, they'll do something like that. Well, the fact of the matter is that we don't have to stop completely emitting carbon dioxide. What if we can just cut our excess? So we are emitting 9 gigatons. 5 of those 9 gigatons are being removed by natural processes. So why don't we cut down from 9 to 5? Yes, that's a 45% drop in carbon emissions. That is a very, very ambitious goal. But whenever you hear somebody talk about carbon neutrality, what they're talking about is getting us to a point where the amount of emissions that we put into the atmosphere are actually being offset by these other processes that are either being removed via photosynthesis, being removed via phytoplankton activity, or being removed via the oceans. Now, of course, the 2 additional gigatons that we're adding to the ocean, that's also problematic because it's acidifying our ocean. But if we can bulk up photosynthesis so that maybe it can take on an additional gigaton, that may actually put a little less pressure, a little less weight on the ocean. And so really, when talking about how we as humans are actually going to fix this problem, the answer isn't stop emitting carbon dioxide. The answer is a share between reducing our emissions while actually beefing up components of the Earth system that can actually take those emissions away. So less sources, more sinks. If we can find that magic combination, and it's really hard to do, it'll make all the difference in the world. Hi, Alexis. You unmuted yourself. Did you have a question? Hello? I guess not. Okay, not a problem. So let's talk about how we're actually messing this up. Why is it that we are putting more carbon into the Earth system than it can cope with? Well, the reason why that happens is because there are 2 main legs of the carbon cycle: the short-term cycle and the long-term cycle. So first, let's talk about short-term cycles. Obviously, the most obvious short-term cycle, and you all did a really good job of mentioning this in the warm-up today, photosynthesis versus respiration. That is a short-term cycle. That is a short-term cycle. Right now, as we speak, especially now that the sun is coming out, at least some of the plants and trees right now are going to work. And what they're doing is they are absorbing carbon dioxide from their surroundings. They're drinking up a little bit of water, which is why we need to water our plants. And then they're reacting with sunlight to produce sugar and oxygen. Well, at some point today, I would assume that, well, I always want to be careful with how I say this, but I assume at some point today or some point, you're going to eat something. You're going to consume something. You're going to eat something. I really, and forgive me if that's a bad assumption, but you're going to eat something. You're going to intake some sugar, and you're going to breathe in some oxygen. So what you are, in a very real sense, what you're actually doing is you're taking what the plants shoot out, and you yourself are consuming it. Even if you're eating a big chunk of beef, guess what? That beef was fed plants. So it may be an extra step, but it still gets to you. So in this case, humans are consuming the sugar and the oxygen that is released by these plants, and on the other end, exhaling carbon dioxide water. Yep, your breath also has a lot of water in it, and energy. So if you take a look, in essence, what went into the plant is what comes out of you. And then guess where it goes? In many cases, right back to the plant. This process doesn't actually take very long. This process doesn't actually take very long. And in fact, we can even see its effects, its impacts in the Keeling curve. I've called this the Bart Simpson's hair analogy before. I know that you've all heard me say that already. The Bart Simpson's hair analogy. And basically the idea there is every single year, carbon dioxide concentrations go up early in the year. Then they peak roughly around April or May. There's a slight lag. Then they take a big drop in the summer months. Then they bottom out. They bottom out roughly right about now, right around October. And then carbon dioxide concentrations go up again. This is all due to that balancing act between what is being taken in by plants and what is being exhaled or respired by Mother Nature. During the spring and summertime, there's more going in, or actually, let me rephrase it. There are more sinks, there are more things that are absorbing carbon dioxide from the atmosphere, taking it out of the atmosphere, than there are releasing it into the atmosphere. And so during those months, carbon dioxide concentrations go down. Then we get into fall. Trees go to sleep. They stop doing photosynthesis. They take their break. We're still eating. We're still breathing. Same thing's happening with organisms all around the world. So during those months, there's actually less going out than coming in. Carbon dioxide concentrations go right back up. I'm actually going to skip this, but over one calendar year, what months are atmospheric concentrations highest and lowest? Well, they're typically highest in fall and winter, and they're lowest in spring and summer. Once again, it's because in fall and winter, photosynthetic activity is reduced, while respiration typically goes up a little bit. Many of those same plants and trees that were sucking in carbon dioxide actually are releasing it during fall and winter months. So fall and winter months, highest. Spring and summer months, lowest. And then what factors contribute to this annual cycle? Why do they go up and down over the year? Well, it's all because of that balancing act between photosynthesis and respiration. So that's one example of the short-term carbon cycle. That whole process takes seconds in me inhaling oxygen and exhaling carbon dioxide to maybe a few days, plants taking that carbon dioxide, taking it in, converting it to sugars. That process is pretty quick. That process is pretty quick. And it does have a seasonal cycle to it, once again, because during the spring and summer months, there's more photosynthesis happening. So in the spring and summer months, CO2 drops. CO2 drops. During fall and winter, there's more respiration. Carbon dioxide goes right back up. So this is one example of a short-term carbon cycle. And this basically just details the steps that I've just talked about, the process of photosynthesis and respiration. When plants photosynthesize, they are taking carbon dioxide and water and converting it into sugar. Interestingly enough, that sugar contains energy. And it's actually sunlight that provides that energy. So when I said a few weeks ago that 99% of all incoming sunlight, or sorry, 99% of all of Earth's surface energy comes from the sun, even the foods you're eating right now, or earlier today, or later today, or anything that you eat, believe it or not, contains energy that was at one point sunlight, that was converted into something else via photosynthesis. And then oxygen is another byproduct of that. Yay, it's waste for the plant, but it's good for us. So one thing's trash is another thing's treasure. And then these plants use this energy, these sugars, to grow. Eventually, unfortunately, the plants do die. When they die, that carbon that they're holding on to is released into the atmosphere. So when they die, all of that carbon that they took in, unless it's consumed by humans, unless something else comes along and eats it, that carbon is just returned to the atmosphere. There's more photosynthesis once again in the spring and summer months, more respiration once again in the fall and winter months. And as I indicated right here, during spring and summer, CO2 levels go down. Fall and winter, CO2 levels go up. So that's one example of a short-term carbon cycle. Other examples include things such as dead organic material. So when something dies, I know that that sounds depressing, but when something dies, little microbes, little bacteria will actually begin feasting on that something. I know that sounds really, really bad, but it happens. And one of the byproducts of that feasting is oftentimes the release of methane and carbon dioxide. Organic matter also decays by itself and releases carbon. And then, as I mentioned earlier, our surface oceans are also a key component because our surface oceans, specifically phytoplankton, perform photosynthesis. So our surface oceans are also taking in carbon dioxide and releasing carbon dioxide pretty continuously. So they're adding and removing carbon dioxide pretty continuously. And in fact, all short-term carbon cycles are pretty much doing that. They're adding and removing carbon dioxide pretty continuously. Right now, as a plant outside is taking in carbon dioxide, I'm exhaling carbon dioxide. The truth is, the short-term carbon cycle isn't really where we've messed up. The short-term carbon cycle is not where we have messed up. Where we have messed up, and so a lot of these different components of it. So people taking in oxygen, exhaling carbon dioxide being emitted by the burning of fossil fuels. This right here is a short-term process. However, this is an artificial short-term process. What I mean by that is we have actually screwed up, not the short-term carbon cycle, but actually we have screwed up the long-term carbon cycle. Because fossil fuel emissions release carbon dioxide like that. If that carbon dioxide, however, was left to itself, or if that carbon, those fossil fuels were left to themselves, that same process, that oxidation of dead fossil fuel material, would actually take millions of years. So what we have done is we have essentially taken a long-term cycle and we have added it, we've made it a short-term process. And that's one of the reasons why we are adding more carbon dioxide into our atmosphere than it can cope with. We're adding more into the system than it can cope with. And the reason why is because we have introduced fossil fuel emissions into the short-term cycle. Now, how does this actually, what have we screwed up exactly? We haven't screwed up a short-term cycle, these different components of the short-term cycle. What we have is we've actually screwed up the long-term carbon cycle. So everything I've talked about in terms of carbon right now has all been short-term. Sorry, I have a frog in my throat. But what about the long-term cycle? Because this is where we have really screwed up. So unlike the short-term cycle, the long-term cycle is much, much slower. It doesn't just go, carbon makes it to a plant, gets sucked up by the plant, shoots it right back out. It doesn't do that. Instead, it is way more gradual, way slower, way more gradual, but it's still continuous. Some examples of this include what's called chemical weathering. Chemical weathering, which actually creates limestone, absorption into the oceans, the burial of dead organic material, Earth's crust. These are different portions of the Earth system that are present in the long-term cycle. Whoops, sorry. As I mentioned, these processes take a very long time. So unlike the process of me exhaling carbon dioxide and a plant nearby taking it in, these processes take millions of years. There are actually two main components to the long-term cycle. The two main components are chemical weathering, which results in subduction and volcanism. This is actually one cycle right here. The second cycle, organic carbon burial, and then oxidation. This is the one we're screwing up. We are screwing, as a weird looking C. This is where we're going wrong. This is where we're going wrong. So let's actually very briefly, I won't be able to finish this today, but let's very briefly look at each of these legs of the long-term carbon cycle. So there are two main legs. There is, whoops, the carbonate leg over here, where via chemical weathering, we get limestone that's created. Limestone eventually gets subducted into the earth and eventually becomes liquid hot magma. And shooting out of that liquid hot magma includes a lot of carbon dioxide. That carbon dioxide in the atmosphere, though, actually gets absorbed by rain. Somebody who mentioned that rain takes carbon dioxide out of the atmosphere, bingo. And that rainwater then actually converts silicates, which are basically rocks, to carbonate, which is limestone. It's what chalk is made up out of, or made out of. So this is one of the two legs. The other leg is the burial of organic carbon. In this case, things die, things get buried. Over time, more stuff builds up on top of them. All of that dead organic material gets compressed and it becomes a fossil fuel. If left alone, it would take millions of years for that fossil fuel, for that dead organic material to oxidize. It would take millions of years for all of that to oxidize. But, so this should take millions of years. Should take millions of years. But we have sped it up. We have sped it up. Should take millions of years, but we have sped it up. How have we sped it up? We'll talk about that next time. So that's it for today. I'll wrap up a couple of minutes early. And then what I'm going to do next time is I'm actually going to talk about how each one of these processes works. And then we'll get into the good stuff, which is how have we screwed this up? How have we sped this process up? So that's next time. Until then, I will actually get those participation points put in the grade book. In fact, I'm actually going to do that right now. So it may take me a few minutes, but you will see those in there pretty quickly. Otherwise, if you have any questions, comments, concerns, threats, I can hang out for a few moments, and I will see you all on Thursday. Bye.
Thank you.
Bye.
Thank you,
Thank
Professor.
you, Professor.
Thank you. Have a great day, everybody.
Thank you.
Bye. Alrighty. If anybody has a question, I'm still here. If not, I'm going to sign off in a minute, but I'm still here for the moment.
For the last lecture, I entered kind of late because of technical difficulties, and it totally slipped my mind to ask you for the participation question. Is it too late to get that now?
Yeah, why not? I'll send it to you. Let me,
Thank you.
give me one moment. Let me pull it up. And this will just take me a second. Okay. Met 12 participation questions. And let's see here. That would be October 1st. And here you go. Let me paste it right here. There you go.
Thank you.
Absolutely. Is there anything I can help anybody else with? Alrighty, well, I'm going to sign off for right now. If you have questions, please don't hesitate to email me. I'm going to get those participation questions logged into the gradebook really quickly. And have a great day, everybody.